Now coming to the coaxial capacitor. So now let us take a coaxial line. It consists of inner conductor and it consists of outer conductor, right? So inner conductor and outer conductor forms a capacitor. The space between inner conductor and outer conductor is nothing but dielectric medium. The whole structure forms capacitor, that is called coaxial capacitor. Inner conductor radius is A and outer conductor radius is B. An interconductor has charge, positive charge, and outer conductor forms as negative charge. The voltage at inner conductor is V1, voltage at outer conductor is V2. Okay. So here magnetic flux around the inner conductor is formed. That so that is in the form of a circle. That is it is having radius rho. That rho in between A and B. Right. So magnetic field around the inner conductor is formed. It is just like a cylinder, right? It is like a cylinder. Okay. So through that cylinder, how much flux is coming? We can calculate by using Gauss law. That is Q is equal to epsilon into surface integral A dot ds equal to epsilon into. So what is close to surface integral? It is coming through the front direction, top direction, and bottom direction. In top and bottom direction, there is no flux. Flux is coming through only front direction, that is in the direction of rho. So it has only E rho only. Rho component of the electric field is there only, right? So we have only P is equal to epsilon into A rho into ds. Epsilon into E rho integral to ds. So what is ds? Okay, see, ds is nothing but rho d phi dz. Rho d phi dz. So it is in the direction of the road, in the direction of the road. So differential surface area in the direction of rho. Okay, so we calculate flux in the direction of the rho. That's why we take a differential area in the direction of the rho, right? So if you integrate this one, so if you integrate this one, d5 0 to 2 phi, and z limits, that is the length of the coaxial line, so 0 to L, lower limit is L and L. So what you are getting electric field intensity, what the flux is going to, what is the integration total? Integration is E epsilon into E rho into rho 2 pi L. So this is nothing but a enclosed charge is equal to Q. Q is equal to, we got that one. From this one, so E rho is equal to Q by epsilon into 2 pi rho L. So E is equal to Q pi epsilon into 2 pi into rho L, it is 0. So you know the voltage is equal to minus line integral 2 to 1 u dot dl. So voltage is difference between two voltages V1 minus V2, V1 minus D2, V1 minus V2. So V1 minus V2, the lower limit is 2, upper limit is 1, E dot dl. So lower limit is B, that is voltage at second conductor, that is radius B of the outer conductor, and V1 voltage at the first conductor, inner conductor. So the its radius is A. So we have to take the limits B to A dot dl. If you substitute electric field intensity, whatever derived here, substitute here Q by epsilon 2 pi rho L, that is in the direction of the rho, and dl is also in the direction of the rho, so d rho into a rho. So in entire term is treated as a constant minus Q by epsilon 2 pi L. Take the integral b to a, and 1 by rho is the integrable integration variable 1 by rho d rho. So what is integration of the 1 by rho is log rho. Apply the limits b to a. If you apply the limits, you will get log of a by b. So here we have minus. If you take it minus out into the logarithm, it will become log of v by a. So we got the voltage formula q by epsilon into 2 pi L log of b by a. Right? Now you got voltage and C equal to Q by V, and substitute voltage formula in this here. So what is V? We got Q by epsilon into 2 pi L into log of B by A. V by A. So finally it will become epsilon into 2 pi L by log of V by A. So finally C equal to 2 pi epsilon L by log of B by A. So this is about capacitance of the coaxial capacitor. So coming to the spherical capacitor. Spherical capacitor means it consists of two concentric spheres, two concentric spherical conductors as in here. Okay, so inner sphere having radius A, outer sphere is having radius B, right? So inner sphere and outer sphere, they are separated by dielectric medium whose dielectric constant is epsilon, right? So here the magnetic flux is around the inner sphere or in between the inner sphere and outer sphere. So you have to take the area of this, you have to take the surface area of this magnetic flux, so that as a Gaussian surface area, as a Gaussian surface area. Now let us see. So you have to apply Gauss law. I would apply Gauss law. So apply Gauss law to the spherical surface whose radius is rho, right? Q equal to closure line integral of d dot ds. So d is E into epsilon. So E closure surface integral E dot ds. So here electric flux lines around the inner sphere. So that surface area in the direction of the R direction. So you have to take only R component only. So here is the constant, and you have to take integral ds only. So what is the surface area covered by that magnetic flux, that in the form of spherical, that is 4 pi r, that is 4 pi r. So epsilon er into 4 pi r. Okay, so what is this area? This is area of the magnetic electric flux around the inner sphere. Around the inner sphere, you see the sphere. Okay, this my electric flux around the inner sphere. So that is in the form of a sphere whose radius is r. So what is the area for this surface area covered by this, covered by the electric flux, that is in the form of a sphere. That is in the form of sphere whose radius is r. So you have to take the area of that sphere formed by the electric flux. So that is, what is the area of the electric flux around the inner sphere is 4 pi r square. Directly you can write, or you can take the integration, or you can substitute directly 4 pi r square. So E is ER is equal, you can write Q by 4 pi epsilon r square. So E equal to Q by 4 pi epsilon r square to AR. So that is in the direction of ER. Now you know the potential difference between two spherical conductors. So V equal to V1 minus V2, line integral